Okay, so the main topic of today is something called intermolecular forces. So the intermolecular forces are forces between molecules. So there are also, everything we've done up until this point is something called intramolecular forces that are forces inside of a molecule. So that's what's holding like these Lewis bonds and structures that we did before. So what's holding methane together, all those carbon-hydrogen bonds, those are covalent bonds, those are inside of one molecule. And that's an intramolecular force. What we're going to look at today are the intermolecular forces, how one molecule interacts with the next molecule beside it. So how the molecules in a whole soup of molecules, how they interact. That's the goal of today's lesson. So they affect different properties that we can measure. And the ones we're going to focus on specifically are melting and boiling points. Oh, jeez. Boiling points. So basically, is it like how much energy does it take to boil something? And for some compounds, it's very easy to boil them. They are gases at room temperature. Or some things are really, really hard to boil that take in a ton of energy. And so we'll be looking at the melting and boiling points of different compounds and the kinds of forces inside that molecule that makes these make sense. Okay. Remembering from the last lesson of electronegativity, how bonds can be polarized. So as polarization just means more negative or more positive. That's what polarization means. As bonds become more polarized, the charges on the atoms increase. So there's more charge on an atom. So if you get more polarization, there's more pluses and there's more negatives being in different places. One side is more plus than the other side. This increases all the boiling points. And the basic premise of all of this is that positives really like to hold on to negatives. They're very good at it. And so the more positives and negatives you have in a compound, the more they're going to hold on to each other. And so we're going to look at the differences between that property. So starting at the strongest thing that holds itself together is ionic forces. And they hold, very creatively, ions together. So when you have ions, an ionic force holds them together. So those of us that know physics, we can know that these electrical charges actually have a force between them. That electrical force follows something awesome called Coulomb's law. Yeah, Coulomb, French guy. That's probably why I'm probably saying his name wrong, but that's how I've said it for years now. We're going to go with it. Coulomb's law increases with charge. So if there's more charge on an ion, that's more force. And if there's more distance, that's less force. So if you got lots of charge and you're really close, that's a lot of force there. But if you have less charge and more distance, that's less force. That's all we're going to go into Coulomb's law of force. That's a whole chapter in Physics 12. So we'll get into the details of that if you take that course. But for us now, more charge, stronger, more distance, less strong. That's all we need to worry about at this point. That's it. We're not even going to put math on it, just more and less. That's all we're going to do. No numbers. Okay, strong attractions between these ions. So our classic ionic compound, everyone's favorite, Na and Cl. I'm going to draw them like this. Remember how we draw our NaCl like this? What charge does a sodium that has lost its electron have? What charge does a sodium have when it loses its electron? Its valence electron. It has a positive 1 charge, right? One sodium missing an electron has a positive 1 charge. That chlorine stole sodium's electron. What charge does it have now? It has -1. So we have a +1, -1 charge. And those two full electrons worth of charge per molecule just really hold themselves together. So sodiums, salts, NaCl, melting point. So we're not even at boiling points. You can boil it, but it's a lot. So melting, which we can do, is 801 degrees, not 80, 801 degrees Celsius. So if you get table salt to 801 degrees Celsius, it will melt. You get a liquid salt. So these ionic compounds have high melting points. And even more ridiculous boiling points. We're not even going to discuss them. They're in the 1500s. They're getting very, very hot before you can boil them. But yeah, we're just going to stick with those. So this kind of covers all of the different ionic compounds. We can do things like a lithium and a fluorine, right? It's basically the same pattern. I'm not going to draw too many of these. Are lithium and fluorine big or small? They're both very small, so they can get really close together. So they actually have a really strong charge. Melting this will be also really high. Both of them are pretty small. Let me put those little positives and negatives on them too, keeping the same color structure that I've done. So they can get really close, and so their attractions are really long. I'm going to draw something else. And it's going to be a little less, but still more than everything else we're going to talk about here. So if I do one of these, and I'm just going to leave it here as NH4. We can do the Lewis diagram on NH4. It was one of your questions in the practice from last week. But I know NH4 is the ammonium ion, and so I know it has a positive charge. Just looking at my ion sheet from the periodic table, I know it has a positive charge. And if I stick it to something big like an iodine, and put the dots around my iodine. Now we know iodine is big. It's at the bottom of the table. It's number 53. It's got a lot of layers to it. So a single iodine has a lot of space. It's a big ball of molecule there. And NH4 is actually 4 atoms or 5 atoms worth of molecules. So they're even bigger and spread out. So the boiling point, or in this case, melting point, is going to be less. Right? Those ions aren't held quite as tight together because they got all this space taking them up. Does that kind of make any sense? So yeah. All right, so now that I've looked up that one, you're not going to be actually predicting them, you're just relating them together. Like, you would know this one is going to be lower than this one and this one. These ones are also really going to be really high. What is the lithium? Fluoride. Yeah, 848. So these two are really, really tightly held because they're very small. This one, because it adds some space, is a little less. So the less tightly, lower melting points. That's the main goal there. Pause. Okay. The next interaction is a little less. It's called hydrogen bonding. And it occurs when highly electronegative elements are directly bonded to hydrogen. So highly electronegative. So when we get our really high electronegative elements bonded with hydrogen, they're so imbalanced that they actually create a decent amount of charge. So hydrogen is much more electronegative than others. So I'm going to draw a few of these. Just a second. I'm going to get our organic chemistry brains going here. So those of us that are perfectly remembering our organic chemistry brain, what do I have here? Anybody? So the things that I want to show you about. So oxygen is highly electronegative, right? If you guys have your notes from Friday? Yeah, you have the table of all of them on there. Oxygen is really highly electronegative. It's got all those dots on it from its Lewis structures. Let's put the Lewis structure dots on there. And it's got this lovely symbol here. Remember, what's that little squirrely? Looks like a cherry. It's called a delta. So it's a delta minus there. And since we actually have hydrogen is at a delta plus in this case. So oxygen is basically pulling all of those electrons close to it. So the electrons that are shared between the oxygen and the hydrogen are almost all the way to the oxygen. Not all the way. All the way would be like the ionic compounds above. I fully took it. No, I'm just going to share it mostly. So that's ones there. Other ones are like 1, 2, 3. Let's do 2. Let's do this one. So just a simple one of those. OH Lewis diagram for this thing. And it's going to be a delta minus on this one and a delta plus on this side. So the oxygen is stealing all of these things. We can even get like really crazy and we get this FH nonsense here. And remember, fluorine has got all of these electrons over here. Fluorine is the most electronegative element, and so it's stealing almost all of the hydrogens, but not quite all of them. So this is a huge difference without being one whole electron. So the electron that's hiding in these two little dots, it's like almost here, but not quite. So it's not a full ionic bond, but it's as close as you can get without being an ionic bond. Hydrogen is a lot more electronegative than other group 1 elements. Like if you look at the column where hydrogen's in the column 1 with lithium, sodium, and potassium. Lithium, potassium, and sodium are going to lose that electron. They're not going to hold on very well. They don't want it. They want to get rid of it. Hydrogen wants it a little more than those other ones. So as much as fluorine and oxygen want to take it away, hydrogen wants to hold on more. It doesn't want to give it up. So that's why we're not getting this full ionic pattern here. And so they're less polarized than ionic bonds. They have some covalent character. So they are covalent bonds. They're kind of a mix between covalent and ionic bonds. Okay. So these things share really unevenly. Hydrogen's much more electronegative, 2.2 compared to the other ones, which are all less than 1. So they're less polarized than ionic, but more than other covalents. Dipole. Okay, let's pause. Do you guys know what dipoles are? Back to this. So the dipole of one molecule actually can align, pen back on, align with the dipole from another molecule, adding to increasing attraction within the solution. So we're going to draw this interaction on the next page just because that's running out of space here. But the idea here is that the positives of one molecule are going to interact with the negative part of the neighboring molecule, and they're going to hold together. Basically, that's the idea. So I'm going to give my best shot at drawing this thing on our next page, and we'll work from there. We're going to draw some alcohol structures because they have good hydrogen bonding in them. So some alcohol structures I'm going to draw like this. 1, 2, 3, O to H. And then I'm going to draw this O roughly here. O dash H, same molecule. And I'm going to draw it similar down here like this. O, H, down like that. There we go. Okay. So what we're going to get between each of these molecules is this going to have a little bit of bonding along the line here. So these are going to really hold on to each other. The O's of one molecule are going to want to hold on to the H's of the next molecule over. So we're kind of creating this grid of hydrogen bonding. And then, obviously, this is a three-dimensional solution. It's all mixing together. And so I'm drawing it like as a flat way, but that's not perfect. It's just the best way I can draw it on paper. But also, there's other molecules on this side. So I can also draw like an O, oops, not that color, let's keep it the right color. I can draw an O to an H over here and have the molecule kind of coming up that way, I guess. Let's draw it the same. And so then I have also this interaction on this side, right? So it's this three-dimensional attraction where all of the negative parts of one are holding on to the positive parts of another. And so numbers-wise, we'll put through a few numbers to compare. So when we do a methane, right, a nice simple, what is I'm doing here? 4 is the number we're looking for here. So a methane has no hydrogen bonding. Right? Carbon wants to hold on to that electrons, and then hydrogen's roughly the same. They're not really all that different, so we're going to say they're the same. It's got a boiling point, which is how we say boiling point, of like negative 161 degrees Celsius. Which feels right? That seems ridiculous though, right? What does that negative boiling point mean? It means at room temperature, methane is a gas, and it takes down to 161 degrees below zero before it will start condensing into a liquid. You can get liquid methane, but you got to get it real cold first. So that's the boiling point of the no hydrogen bonding methane. Something that has a lot of hydrogen bonding is water, right? Water, which is H2O, lots of O's, lots of H's, really like to work themselves together. What's the boiling point of water? 100 plus, so it's plus 100 degrees Celsius. It's a liquid at room temperature, and you have to heat it up to get it to the gaseous state. As far as size is the other thing that affects boiling points, which we'll get to at the end. These two molecules are roughly the same size. Methane has a weight of 16, water has a weight of 18. They're roughly the same size. And so their differences in their boiling points are explained through the hydrogen bonding. The water really likes to hold on to itself. You can see this with the surface temperature of water. Water loves to stick to the side of containers. It really likes to stick to itself. It makes little droplets. When it falls from the sky, it makes raindrops. It likes to hold on to itself a lot. And so it takes a lot of energy for it to break that apart. And so this is the hydrogen bonding arrangement. And so that's how that kind of makes sense. Okay, the next interaction is we're getting weaker and weaker. And these are just our general dipoles. So when we were doing the electronegativity stuff from last lesson, you were just listing polar covalent compounds. So these are the polar covalent compounds that are just not nearly as strong. So they're polar covalent, but they're less. But with strongly electronegative, but not quite as much. So it's like hydrogen bonding, but less. I think I gave you a blank and didn't make a blank on mine. Did I forget to do this? Did I do this like in 2 different stages? Oh no, all that's written in there properly. Okay, so yeah, it's basically like hydrogen bonding, just less strong. So there's just less difference in this case. Oh, that's not me. Okay, next one. So these dipoles interact with each other to increase boiling point, but less than hydrogen bonding. So there's still some interaction. There's still a positive and negative side to these molecules, but less than the hydrogen ones, so it's just less of an effect. So I'm going to draw a few of these, and we'll, I think the site I stole this mostly from was teaching it in the context of organic chemistry, so all of my examples are organic chemistry compounds, but that's good because there's a lot of variety in them. So if I just draw a very simple one, like we can do H3C, and we've got, if we do the finish up the Lewis with a whole bunch of dots on that side, we know that O is going to steal or at least pull on those a little stronger, and we're going to get a little bit of positive here on this C, right? So there's going to be a little bit of the carbon's going to be a little bit positive because all the oxygen is going to try to steal these electrons away. So the double bond is going to be more to the oxygen side than to the carbon side. So it's just an unequal sharing of it. So we can also do like a crazier one. I like doing crazier ones. H3C, CH3, double bonded to nitrogen over to a methyl group. I'm not going to ask you to name that one. You probably could name the first one, but you're not going to name this one. Based on all the things we've learned about electronegativity and compounds, where is my little bit of negative going to show up on what atom? Which one is the most electronegative of them? The nitrogen, the one that's different. So nitrogen's going to get a little bit of negative, and then the carbon in the middle there and the carbon up top are going to get a little positive on each side. So we're going to get a little positive over here and a little positive down there. So a little bit of positives on that one, a little bit of positives on the two carbons on each side. So instead of sharing those bonds equally, nitrogen's going to be pulling those electrons in. It's going to create a little bit of negative side. So we're still going to get this overall interactions, but they're just so much less than the hydrogen bondings. They're pretty less. But still some interaction. They're not completely non-polar. Okay. Stop. Record again. The next one are called London dispersion forces. These are also called van der Waals forces. They're just basically the effect that polarity has. So basically, these kinds of compounds, or even atoms themselves, have essentially no dipole. So these are the interactions where they're non-polar covalent compounds, or just straight up non-polar elements by themselves. But if we think of a soup of electrons, they can have one side be more negative than the others at any one instant. We can kind of like, they're moving around really fast, and so at some point, they're imbalanced. Think about if you've got a big raft, and instead of everyone spaced out equally, holding the balance set, we're going to say, run around on the raft. And at some point, there's going to be more people on one side of the raft than the other, and it's going to tip a little bit, right? And so that will create a momentary imbalance. And so we call that momentary imbalance an instantaneous dipole. Oops, let's turn the color back on and do dipole. So basically we get this instantaneous dipole. Like there's at some point too many electrons on one side and not enough electrons on the other side. And so we get this imbalance of electron distribution on one side of the element than the other. And one side, it can be more negative than another side. Where? Oh, my, like, almost another D again? Yeah. Let me clean up that word dipole here when I turn on the eraser and don't just highlight it. That says dipole on it. Okay, so I got a space down below. I'm going to draw a little bit of this dipole. So basically what I want to do is I'm going to draw a really big atom that's pretty neutral. I'm going to draw a krypton. Right? Now, normally krypton is going to be pretty evenly negative around the outside. I'm just going to draw a few of them. Krypton has 36 electrons. I'm not going to draw 36 electrons. I'm just going to draw like 6. Just going to draw them around. And normally krypton is essentially balanced. It's this big, noble gas, doesn't do anything. But at some point, there could be a time where the krypton kind of has too many negatives on one side, and then the other ones are more spaced out over here. So they're like just too tight on one side. And so what we get, let's clean that up a bit. Let's go, eraser on, and let's slide those over. Let's just get really outside with that. So basically I get one side is going to be too negative, and this side is going to be a little positive. And so we get one side of our molecule to be more negative than the other side, and so when it finds another one, it will stick to it a little better. So this does basically account for the weakest of all the forces. This isn't really increasing the boiling point. It's just basically creating a boiling point at all. You can cool this down enough to liquefy. It's really cold, but it's possible. So there at some point need to hold on to each other. One krypton needs to hold on to the next krypton, at least a little, or it would never liquefy. So there is a point at which you can liquefy these noble gases or these, what's it called? These non-polar covalent compounds. They can be condensed, but it takes a lot. It takes a lot temperature needs to get really far down. And so this is the weakest kind of interaction. If this was not possible, they would never condense, and even at absolute zero, they would still be a gas, which kind of doesn't work. It just explains the lowest part. Okay. I'm going to move on to the next page because it kind of just continues on to the next page there. I'm done the drawing, just where the gap was. So on the next page, I'm going to explain all that stuff. So the term, the one we call this, is this fancy word that's written right below. It's not really much of a spoiler. It's polarizability, which is a heck of a word. Polarizability. It's a lot of syllables, and it describes how these elements can form these dipoles. So basically, how easy is it for one side to be imbalanced versus another side? And that polarizability, really have to slow down when I'm saying that, increases with atomic size. So basically, the bigger an atom is, the easier it is to create an imbalance. It just means there's more things. If you think about a giraffe and there's 4 of you, 1 on each corner, the odds that you will somehow, just on occasion, be imbalanced is weird. You're like, no, we're going to stay right where we are. We're nice and safe. But if there's 50 of you on a huge raft and you're kind of milling about, it's like, yeah, every once in a while, it will just be all imbalanced. And everyone will be on one side and the whole raft will tip over and there'll be problems. But basically, the bigger it is, the more likely it is to get a dipole. And so atoms with really, really very low polarizability, atoms that don't shift very well, have extremely low boiling points. Basically, they're nearly impossible to condense. So I have some examples here. So a fairly big noble gas, argon. So big argon is at negative 186 degrees Celsius. So argon's at a negative 186, which is pretty cold. But we have places and mechanisms to get that cold. We can do that. We can get liquid argon. It's hard, but that's a whole lot warmer than helium, which is negative 272 degrees, which is nearly impossible. Right? How many electrons does a helium have? 2. Just 2 electrons. So they're going to stay like on opposite sides pretty much the whole time. They're not going to be very easily influenced to be both on the same side all of a sudden. That would be weird. So it's almost impossible for us to liquefy helium. We have to mess with it by changing the pressure. We can make liquid helium, but we have to pressurize it, and that changes it too. But this, if we just left it open, we would have to make a container negative 272. Do you guys know what the number for absolute zero is? Like impossibly cold, that all molecules stop and you can't actually get there. It's like a theoretical limit of matter. It's 273. That's the theoretical minimum temperature that you can't actually reach, but that's what it would be if you could get there. It's an asymptotic relationship. But yeah, so 1 degree above absolute zero is where the helium would start condensing because it does not want to form any interactions. One helium has no interactions with the next helium. Okay, but also we want to compare their sizes. So if I take I2, like the iodine molecule, just like one iodine, it boils at 184, positive 184. Iodine is a solid. You can just like have a jar of it. We have jars of it over there, just iodine. But then I have fluorine, right? F2. I just don't have room to write all the letters in fluorine. It has a boiling point of negative 188. So fluorine is very hard to polarize. It has less electrons, so it's hard to polarize. So it's like a nearly 400 degree difference between those two. Iodine at the bottom of the table, very big iodine's 53 versus fluorine's 9. So fluorine's 9 electrons, or I guess when the fluorine molecule has 18 electrons, they're very set. They're exactly where they are. They're not moving. Whereas when iodine, it's got 106 electrons. They're a little more fluid. They can kind of bounce around a bit. They can get a little more imbalanced. Okay. Next line is dispersion forces. Okay. They also get bigger with weight. Right? As I was saying, so basically, the bigger a whole compound is, because it has more surface area, there's more forces, so they have a lowering melting point. No, so boiling point increases. So more interactions, yeah. Increase the surface area. More molecular weight. And then higher boiling point. I'm going to write it in here. So more interactions, harder to boil. Or easier to condense. Same idea. Harder to boil, easier to condense. So higher boiling points. So I'm going to do a few of these things here. If I do, we did it before, but I'll just go CH4. I'm going to be lazy. My notes have it all written out in words. I'm a lazy person. It's minus 164, as we said before. C2H6 is minus 89. C3H10. Trying to remember how to do my alkane formulas. It's negative 42. C4. I think that's actually supposed to be 8. Isn't it supposed to be 8? Why is it? It's 8 because it's 6 plus 2. So it's 8. Let me erase that. It's definitely supposed to be 8. You can't actually make this thing. It's 8. Sorry, guys. 8. C4H10 is negative 0.5. C5H12 is 36. And the last one I'll end up here is C6H14 is 69 degrees. So these are all in degrees Celsius. So basically this is just trying to show that like as they get bigger, their boiling points increase. They hold together better. They hold together better the bigger they are. And these are all alkanes. These are non-polar bonds, right? This is a non-polar things. So this is methane, ethane, propane, butane, pentane, and hexane. So these are just the 4. It goes all the way up to octane, which is 125. I didn't get that far. I ran out of page. That's enough. We got the point. It's getting bigger. It's getting warmer. That's what we're doing. So that's the last thing I want to say here. Oh, and then the summary. Basically, strength of interactions goes in this way. Ionic is the strongest. Ionic. Stronger than hydrogen bonds. Which is stronger than dipole interactions. Dipole, dipole interactions. And then we have London dispersion. And that's their basic impacts on their boiling points. So ionic bonds held together extremely tight. Hydrogen bonds do hold really tight around each other. And then we have dipole-dipole interactions, holding on okay, and then London, like barely anything. Just the lightest little hold on each other. That's their difference. So this is a very, very like arm-wavy, theoretical kind of lesson, just basically describing these forces. And so based on the kind of electronegativity, based on the kinds of bonds that you were describing in the last lesson, you can predict whether a certain chemical will have hydrogen bonds, it will have dipole interactions, and then you can predict its relative boiling point with another similar compound. You can go look, oh, this one will definitely boil higher than this other one based on these kind of properties.